this lesson is going to focus on a way to calculate enthalpy using molar enthalpies and in particular the calorimetry method. So we like to use the calorimetry method when we're carrying out a chemical reaction, and particularly in a lab setting, like we're going to carry out a chemical change or a physical change. And we recall that it's hard, really hard, to measure the enthalpy of a system directly. But what we can do is we can measure the heat of our surroundings because we know that there's an exchange of heat between system and surroundings. But we are still going to incorporate the system. So this is a little bit of a different change than our heat calculations in our previous lessons. So when we carry out chemical reactions, that amount of heat is either released or absorbed, and it's dependent on the mass of the substances in the system. We know this. So we also know it's also based on the mass of the surroundings as well. But now with enthalpy, we have to incorporate the system. And the system is always described as these thermochemical equations that release or require a certain amount of energy be either created or absorbed based on the mole values of your substances in the overall system. So we have to now go back and figure out mole values of particular substances in our system. So we are going to be using that original formula that we've used, right? Q equals mc delta T. We know that that formula is used for the surroundings. We're going to throw a positive or a negative in front because, again, whether the system is exothermic or endothermic, that's going to relate to it. And then we have to apply an actual mole value of one aspect of our system. It might be a reactant, it might be a product. It's whatever information they give you in these particular scenarios. So today's formula is kind of a blend of the heat formula that we used with surroundings, plus now we're incorporating specific mole values of the system. And using the technique of calorimetry really allows us to do this. We can measure the heat change or the temperature change of our surroundings, and then we can use that data to calculate whatever it is that we need to about the particular example. So here is a calorimetry example that we can relate here to molar enthalpy. So it says 7.46 grams of potassium chloride is dissolved into 100 mils of water at an initial temperature of 24.1 degrees C. The final temperature of the solution is 20. Okay, so we know right there the temperature of the surroundings has gone down. If it's gone down, that means energy was taken out of the surroundings and given to the system. Okay, so this is an endothermic process. And they're saying, what is the molar enthalpy of solution? Because we're dissolving potassium chloride in water. So we write out our basic formula here. So N delta H of my system. Okay, so this left side is the system side, is going to be equal to plus or minus Q of my surroundings. And the plus or minus Q is going to come into effect later on, okay? It's going to be used to determine whether my enthalpy is exothermic or endothermic. And we know already it's endo based on the temperature change, but we'll leave it till the end. So I have to solve for delta H. That means I got to calculate the moles of my system. And I also have to figure out the Q of my surroundings. So it doesn't matter which one you do first. Let's calculate Q first. Okay, so Q is mc delta T, and this is of our surroundings. So if we just come over here and we put together a little beaker, remember that there's 100 mils of water in here. And what they did is they took some amount of KCl and they dissolved that in water. So the system is this physical change of KCl going from a solid to an aqueous state. The water in my beaker is my surroundings. So let's take a look at this water and get our information that we need to out of it. So what's the mass of my water? Well, the mass of my water is 100 mils. Okay. Do not add in do not add in the mass of potassium chloride. The mass of potassium chloride is the mass of the system. And when you add that 7.46 grams of potassium chloride in here, that is not a liquid, okay? So if it was a liquid, my overall volume of my surroundings would go up. But this is a solid, and when solids dissolve, the only density that is 1 gram per mil is water, okay? Not any other kind of solid. So we have 100 mils of water, and then we remember that that's also equal to 100 grams. So I'm just going to change that and put in grams there. Now, my C is specific heat capacity of my surroundings, which is water. So 4.184 joules per gram degree C. And then my temperature change is negative 4.1 degrees C, right? So the final was 20, and then the initial was 24.1. So we calculate the energy of the surroundings. And when we calculate everything together, we're going to get a value of negative 1715.44 joules. And again, this is now the heat that was taken out of the surroundings in order to dissolve this solid right here. Okay, so this is the system that we're after. So part 2 is I need to figure out the moles of the system. And so I need to figure out the moles of KCl. And because we started with a solid, we're going to take mass divided by molar mass. So our mass out of the equation is 7.46 grams. And then my molar mass of KCl is 74.55 grams per mole. And so I get a mole value of 0.10067. We'll hang on to everything here. Okay, moles. So a difference now compared to the original heat calculations that we're going to do is that, we want to calculate the enthalpy of the system. And this is going to account for some aspect of the system in a molar quantity. When I rearrange that, my third step is going to be delta H of my, actually I can say SOL for solution, okay, because that's what we're doing. We're dissolving potassium chloride. And then I'm going to have plus or minus Q of my surroundings divided by the moles of the system. Now, pay attention to this. This gets a little confusing. We need to calculate the enthalpy of my system. And we know the enthalpy is endothermic. And when we talk about the surroundings, there's a negative term because the surroundings has lost energy. And even though it's lost energy, the system has gained energy. So we kind of forget about that negative sign over on the Q value. And we now are just focusing on the system. So because this is an endothermic reaction, I have to write a positive Q value divided by my moles. So I know it's negative over here, and we ignore that right now, okay? So we're going to write positive 1715.44 joules because we are now talking about the system, and the system's endothermic, which means it's a positive value. And we divide by 0.10067 mole. And then we divide that out, and we are going to round to proper significant figures. So I get a value of plus 17142.90. And we've divided these out, right? So it's now, joules, not kilojoules, joules per mole. Let me erase that for you. That's messy. Joules per mole. And then we're going to round to proper sig figs. So I'm just going to take that and I'm going to divide that out by 1,000 to go into kilojoules per mole. And I need to be aware of significant figures. So I take a look back over here. I had 3 sig figs. Over here, I had 3 sig figs, but here I had 2. So my final answer, because all I've done is either multiplied or divided, has to be positive 17 kilojoules per mole. Okay, let's do another example of enthalpy. So now we're going to have a lab tech take 43.1 mils of concentrated HCl, which we have over here. We see this, that we're adding that now to 475 mils of water. And then we notice that the temperature changes of water goes from 19.2 to 21.8 degrees C. And let's calculate the molar enthalpy. So again, we need our basic formula, which is the moles of the system times the enthalpy. So again, system's always on the left side, will be equal to plus or minus Q. And those plus or minus symbols are just simply to denote for enthalpy, whether it's exothermic or endothermic. We know it's exo. We know that that temperature goes up. So at the end of this, we're going to have a negative term. And that Q is of the surroundings. So when we look at what's happening here, the dilution of HCl is my system. So I'm going to have to calculate the moles of that HCl. And then the surroundings is my water plus that 43.1 mils of HCl that gets added in. Because HCl is a liquid, when I add the two together, the volume is going to grow. And then I take the temperature, the final temperature of the combined volumes. Okay, so we have to be aware here that we have to add that volume in. And we can because this is a liquid. If it's a solid, we don't add them in, but for a liquid, we would. So let's calculate the Q of the surroundings first. So we're going to have MC delta T. Now, the mass of my surroundings is that 475 of water plus the 43.1 mils. So I get a total volume of 518.1 grams. And I know that there's HCl in there, but even HCl is mostly water. Okay, so when we make up these solutions, the predominant substance is water. So we're still going to use specific heat capacity of water. So joules per gram degree C. And then we're going to calculate our delta T. So we have 21.8 as our final, and we subtract off 19.2 as our initial, and we get a delta T of 2.6 degrees C. So let's calculate the overall Q. And we get an overall heat value of 5636.099 joules of energy that is released into the surroundings, okay? So step 2 will now be to calculate the moles of my system. Well, the moles have to be of HCl. And here we go with calculating moles. We know that there's 4 different ways you can calculate moles depending on the variables that you know. Well, I know molar concentration, capital M, and I know volume. And so I have to use the formula molar concentration times my volume in liters, if you recall. My molar concentration is 11.6 mole per liter. And then the volume of HCl is 43.1. Okay, don't add the total. There's no water in the HCl initially. So we divide by 1,000, we get 0.0431 liters. And then we calculate how many moles that will be. And so we get a mole value of 0.49996 moles. So lastly, we're going to calculate the overall enthalpy of my system. And so we'll just write system for now. Here we go, plus or minus Q. Well, it's exothermic. The temperature went up, right, of the surroundings, which means that the system was releasing energy. So that means I need a negative term for my surroundings. So 5636.099 joules. And then I divide that by half of a mole, basically. We'll keep all of these decimals and we'll round at the very end. And then we'll calculate the overall enthalpy. So when you divide it out, you get negative 11,273 point, we'll say 10 joules per mole. And then again, I need to round to sig figs. So back I go to the values that have been given to me. So when I look over here, everything's 3 sig figs. When I look at my Q value, right here, there's 2 sig figs from the subtraction of that temperature. So I need to round this to 2 significant figures. I'm going to divide by 1,000, and I'm going to say that this will be negative 11 kilojoules per mole of heat that is released when I dissolve this amount of HCl into water.